Okay, in this video we'll see the analysis of differential amplifier with active load for common input voltage. So in the previous video we have seen if the input voltage applied is differential, we could be able to find out what is the gain of the differential amplifier with active load. So now we shall find out how do we analyze this differential amplifier with active load, that is the current mirror load, if we apply a common input voltage. So the common input voltage that is considered here is VCM. Here you can see the VCM is applied to both the inputs, VCM as well as VCM here. Of course this is the MOSFET, sorry, the differential amplifier. We are considering a current source, tail current of I. Since we are considering the common input, so we are forced to, or we have to consider a resistance RSS which is coming across the current source, which is a typical resistance. Usually when we are dealing with the differential input voltage, we didn't consider this RSS because there was no current flowing through this particular RSS because of that virtual ground analysis. So since both the current will certainly flow through this particular resistor RSS, so we are considering this value of RSS. So now let us start the analysis. Let us try to write the AC equivalent of this particular circuit. Since if you can see here, this is, I cannot vertically divide this throughout because this half of the circuit is different and this half of the circuit is different. That is, right and left halves are not exactly same. But if you can consider this part of it, since it is RSS, what I can do is I can while writing the current small signal analysis, I can certainly open circuit this and I can ground this and I can replace this resistor on equal side with 2 RSS on either side. Meaning, let me rewrite the circuit with AC equivalent circuit. So I will write this in 3 and I will retain this connection as it is because it is not symmetric over there. I will certainly ground that DC voltage, which is now the AC ground. So this is my PMOS transistor. This is M3. Let me write a resistance of R03 here. This is R04 and this is M4 resistor. Now let me write this as VG3, that is voltage at the gate of third transistor. Let me write this is NMOS transistor M1 having a resistance equal to R01, that is internal resistance. This is VCM. This, now I will split this into two parts, so I will write it as 2 RSS and I'll ground it because this will become AC ground, this will be open circuited. I'll end up with 2 RSS. On the same lines here, for this I will have again same VCM. This is M2 transistor. This is now R02 and I will have again this is 2 RSS, this is VCM. Now if you can carefully observe this, since the value of 2 RSS is very large compared to the resistance what we have seen here, now we will going to have almost the same voltage will be coming over here. So the voltage that is over here will be having the same magnitude. It's almost like a voltage follower. If you want to find what is the current I1 here, so we can certainly find the current I1 with the voltage follower action happening there. The voltage here happens to be VCM. So if this is I1, I will say the same current is flowing here, and let me say this is I2. Let me find out what is I2 is. So you can write I1 as equal to VCM by 2 RSS because the voltage at this point is VCM, which is due to the voltage follower action. Why this is voltage follower action is because you have a very less resistance seen here, and so because we know that, okay, how does the voltage follower looks like. So this is the voltage follower circuit what we are, this is like, okay, CD amplifier. So this is now you have it as AC ground, and if you apply some input voltage here, if you measure the output voltage, if this is your RS value, if RS is too large, so okay, how do we write the expression? The expression for the gain is nothing but, so V0 by V in is nothing but GM RS by 1 plus GM RS, which is almost equal to 1, meaning the output voltage what you're having is almost same as the input voltage here, because this is AC grounded. Now even though this is AC grounded, here this may not be perfectly AC grounded, but the resistance whatever you have here, is very less, which is 1 over GM3 paired with R03. I can approximately write this I1 as equal to VCM by 2RSS, which is the same, because if this is I1, the same current is mirrored here because of this mirror action, so I'm going to have the same current I2 here. You can see now the current I1 is VCM by 2RSS, the same current is mirrored here because of this mirror action. I'm going to have I2 is also equal to VCM by 2RSS. So this is the point where I'm trying to measure the voltage V0, So now let me try to find out what is this current I4, and let me try to find out what is my V0. So I'm supposed to find out what is the value of I4 and what is the value of this R0. Okay, what is the current that is flowing through this R0 for? Now since we are interested in finding what is V0 for this applied voltage, so V0 is nothing but the voltage drop across this resistor R0. If you can see here, so I'm interested in finding what is the voltage drop across this and this. If I measure the voltage drop across this resistor R04, it is nothing but the voltage measured at this point to ground, which is nothing but my V0. So V0 can be written as equal to current through R04 resistor multiplied by the resistance R04. This is my output voltage. Output voltage for a commonly applied input voltage is nothing but V0, which can be found if you can find the drop across this resistor. Drop across this resistor is nothing but the current flowing through this resistor, which we have assumed it as current through R04 multiplied by the resistance R04. Now the point is, we have to actually find out how much is IR04. This need to be found. If I can find this current through R04, then multiply with R04, you can get the expression for V0. If you know what is V0, so V0 by VCM happens to be my common mode gain. Now the entire analysis now is to find what is IR04. Suppose if you consider this node A, I can able to find out, I can write a KCL expression at this node A. So what is that I'm interested is, so this is one current which is leaving the node, there is one more current which is entering, and there is one more current which is leaving. So can I write at node A, suppose if I write at node A, what I have is the current leaving the node is I2 is one current that is leaving, one more current that is leaving is IR04, the current that is entering is I4. Sorry, these are the two currents which are leaving, and this is equal to the current that is entering. So I have the expression I2 plus IR04 as equal to I4. This is the current that is entering, which is equal to I4. The current that is leaving is I2, and one more current which is IR04. But I'm interested in what is IR04, which is now equal to I4 minus I2. I know the value of I2, which is equal to, I2 is nothing but VCM by 2RSS. Now I need to find out what is I4 is. This is what I'm supposed to find out. So I4 is nothing but the current that would flow here. Of course, this is the overall current which is flowing, which is equal to I1. but the current that is flowing through this transistor, of course, other than this IR04, is not equal to I1. That's what we are supposed to find. So now, can we find what is the value of I4? I4 is nothing but, we know that I can able to replace this by, can I able to replace that by a small signal current, small signal model as something like this. This I can rewrite it as R04. This is grounded, and this is what, VG4 into GM4, and of course we are considered this as I4. So shall I now write I4 as equal to minus of this current, because I'm considering this as I4. Sorry, it is not I4, this is actually I4. Is this I4 is equal to minus of VG4 into GM4? But what is this VG4? Is this VG4 is equal to VG3? Because both the gates are shorted, I will write I4 as equal to minus of VG3 multiplied by GM4. This is the expression for I4. So when I have the expression for I4, this is in terms of VG3 and of course multiplied by GM4. But what I want to express is this VG3 need to be expressed in terms of VCM. So let us try to find out what is the voltage at this gate. So can I write the voltage at this gate as nothing but the voltage drop across this equivalent resistance? This is now plus minus. Now we can see here the resistance, what is that we are trying to see now is so what we have now is, can I now write VG3 as equal to minus of I1 multiplied by 1 over GM3 parallel with R03. Can we write it so? You can see this voltage at this point is nothing but opposite of the current, that is I, which is minus I1, which is given as minus I1 multiplied by the effective resistance of this. Because you have gate and drains are shorted, I will going to write the resistance of this as R03 in parallel with 1 over GM3. So that's what is the expression. But what is I1? I can write now VG3 as equal to, because we know that I1 is equal to VCM by 2 RSS. VCM by 2 RSS. Now I can write it as VG3 as minus of VCM by 2 RSS multiplied by 1 over GM3 in parallel with R0. In parallel with R0. So now this is the value of VG3. But what is interest? What we are supposed to find is what is I4 is. So I4 is nothing but of course this is given by minus of VG3 multiplied by GM4. So now this will become equal to, so because I'm supposed to multiply this I4 as equal to minus of VG3 into GM4. What is VG3 now? It is minus of this, so this will become VCM by 2 RSS multiplied by 1 over GM3 in parallel with R03 into GM4. This is the value of I4. So I4 I can write it as equal to, I4 can be now written as VCM divided by 2 RSS into GM4 into, that's what we have, VCM divided by 2 RSS into GM4 multiplied by 1 over GM3 plus, sorry, in parallel with R03. This is what is I4 is. What is I2? I2 we know it's already equal to VCM by 2RSS, VCM by 2RSS. Now what is the value of V0? V0 is actually equal to IR04 into R04. IR04 is nothing but the current through resistor R04, which is written as IR04 multiplied by the resistance. But what is IR04? It is found out to be, of course, that's what we saw here. IR04 is nothing but I4 minus I2. It is now I4 minus I2 into R04. Now I4 is nothing but VCM by 2RSS into GM4 into 1 over GM3 parallel with R03 minus of, this is entire value is R, this is I4 minus of VCM by 2RSS into R0. This can be further written as, I will write VCM by 2RSS as common factor. Of course R04 is there as it is. Now I have GM4 multiplied by 1 over GM3 parallel with R03 minus of 1. This is what is V0. This is what is V0. Let us try to write what is this 1 over GM3. Can I write now 1 over GM3 in parallel with R03 as equal to 1 over GM3 into R03 divided by 1 over GM3 plus R03 upon taking LCM and then simplifying. So I will end up with 1 over GM3 into R03 divided by 1 plus R03 GM3 whole divided by GM3. So this GM3 will go with that. I will end up with R03 divided by 1 plus GM3 R03. So this is actually equal to 1 over GM3 in parallel with R03. So I can use this expression over there. So now my V0 becomes VCM by 2RSS into R04 multiplied by GM4 into R03 divided by 1 plus GM3 R03 minus of 1. So now again let us take the LCM. This is VCM by 2RSS R04 is now GM4 R03 minus of 1 plus GM3 R03 divided by 1 plus GM3 R03. So now this reduces to, of course we are trying to find what is V0, VCM by 2RSS into R04. If we can actually see here, this is R04 into GM3 minus of 1 minus of, this is GM4 into R03 minus 1 minus of GM3 into R03 divided by, of course since you have, I will write it as 1 plus GM3 R03. If the values of GM3 is equal to GM4, in the sense if both the transistors are matched, I can cancel this with, because this is plus, this is minus, this will go with this, and neglecting this 1 compared to this GM3 into R03, I will have V0 is equal to VCM divided by 2RSS into R04, because this minus will come over here, divided by GM3 into R03. If you again assume, because we are assuming M3 is equal to M4 in all the sense, then I can cancel this with this. So now V0 by VCM, which I am considering it as the common mode gain, is now given by minus of 1 over 2 RSS into GM3. This is the expression for the common mode gain of a active load amplifier, active mode differential amplifier, of course, when you are measuring the output voltage single-handedly. This is the expression for the common mode gain, which is given by, of course, which is negative. Negative means it is out of phase, 1 over 2 RSS into GM3. Let us simply go through the entire process again. So actually what we did over here is, since you actually find out what is how do we actually find out this common mode gain is, we considered this particular amplifier with commonly applied input voltage VCM. We actually wrote its equivalent AC signal model. We actually split this RSS into two parts, which is 2 RSS, 2 RSS, which I can certainly able to split only the bottom half of the entire transistor to equal circuit. So this is also, and since the resistance seen at this point is very high compared to the resistance here, so I can certainly write the voltage at the source of this as almost equal to VCM here. So VCM here, so that now I can write the value of I1 as VCM by 2 RSS, which is the current that is flowing here. The same current will flow over here because of this current mirror action. You can see the same I1 is flowing here, and same current I2, which is equal to I1, going to flow over here also. Now we are interested in finding the value of V0, which is nothing but the voltage drop across this resistor R04. Why it is R04 is because you are supposed to measure the voltage at this point with respect to ground. Instead of measuring the voltage at this point with respect to this ground, so it is always easier to measure a easier path. Easier path is if I can able to measure this drop, that happens to be V0, which is equivalent to finding this drop. So since it is complicated here, you choose this path to find out what is the resistance. So we wrote V0 as equal to the current flowing in this direction, which is nothing but I R04 multiplied by R04. So now the intention is to find what is I R04, which is current flowing through this. So we actually wrote a KCL at this particular node. So we consider the currents that are entering. The current entering is only I4. The current leaving are IR04 and I2. So that's what we wrote here. And when we actually wrote what are the exclusive expressions for I2, which we already know it as VCC by 2 RSS. Then we actually try to find out what is the expression for the current I4. So I4 was the current that was flowing in the transistor, that is M4 transistor, because we know that this is the current direction what we consider, which is exactly opposite to VG4 into GM4. That's why we wrote I4 is equal to minus of VG4 into GM4. This is voltage multiplied by the transconductance. This VG4 is nothing but equal to VG3. So we actually found out what is the value of VG3. Now you can see this is the value of VG3, which is nothing but the current that is flowing in the opposite direction multiplied by the resistance. Maybe you may be wondering, while finding the differential gain, we actually considered 1 over GM3 in parallel with R03 as approximately equal to 1 over GM3 itself. So 1 over GM3 itself. But in this case of common mode gain, we are not making the approximation of this resistance of R03 in parallel with 1 over GM3 as just 1 over GM3, because if I consider this expression as equal to simply minus I1 into 1 over GM3, you can see this term is continuing till where? So till it is continuing here. You can see this is 1 over GM3 parallel R03, 1 over GM3 in parallel R03. Suppose if I consider only 1 over GM3, this will cancel with this, so you're going to get it as 1. 1 minus 1 will become 0, then your V0 will become 0. Meaning, suppose if I consider the resistance here as an ideal resistance of 1 over GM, I will end up with the ideal common mode output voltage as 0. Meaning, it will going to completely reject the common signal, which is not the case. So in order to consider the typical resistance which is available at this point, which is equal to 1 over GM3 parallel with R03, we are not making this equal to 1 over GM3. If you write it equal to 1 over GM3, so your entire voltage V0 over here will become 0, then your CMRR will become infinity. So since we want to have some finite value of V0, we are not considering that parallel resistance as equal to 1 over GM3 itself. Okay, let us continue from where we left. So this VG3 was written as minus of I1. Why it is minus of I1 is because the current is going in this direction. I need to consider the opposite direction because this is the drop you are considering. Minus of I1 into the resistance, that is 1 over GM3 into R03. You substituted what is I1. Then we are trying to find out what is VG3 there. So VG3 was found out, and once you know what is VG3, I can find out what is I4 is, which is nothing but minus VG3 into GM4, and then rest is the simple mathematical calculations. We know what is I4, we know what is I2, we know what is the expression for V0, which is IR04 into R04. So we substituted what is IR04, which is nothing but I4 minus I2. So we individually substituted what is I2 value and I4 values. Then you can see this, we retained it as it is, and then we actually found out what is the simplification of this 1 over GM in parallel with R03. This comes out to be this. We replace that over here. Upon simplifying, we are having the expression for the common mode gain of the amplifier as equal to minus of 1 over 2 RSS into GM3. So for this particular differential amplifier with common input voltage, so now we have an amplifier. So now we have a common differential amplifier with mirror load as given by this particular circuit diagram. You can actually find out what is the CMRR of this particular. This is minus VSS. We have RSS as the resistance across the current source. This is VDD, this is V0, and if you consider both VID by 2 plus VCM, this is minus VID by 2 plus VCM, which has got common input as well as the differential input. This is M1, M2, and we are considering this as M3, M4, with the assumption that okay, M3 is equal to M4 in terms of dimension and M1 is equal to M2 in terms of their perfect matching. Of course, assuming R01, R02, R03 and R04 as the resistance of each of the transistor, we found that the differential gain is given by GM into R02 parallel with R04. So this is R02, this is R04, and of course what did we had? So we actually had the expression for the you can see now it is not out of phase, is actually in phase, and we found that AC, that is common mode gain, was given by minus of 1 over 2 RSS into GM4. That's what we got here. Sorry, not GM4, GM3. This is GM3. So this is the expression. Of course, if you consider M3 is equal to M4, then this will become, of course, you can write it as GM3 or GM4. So we can certainly find out what is CMRR in terms of magnitude, which is nothing but AD by AC. AD by AC is nothing but GM into R02 parallel with R04 divided by 2 times, of course now it is 1 over 2 times RSS into GM3. So CMRR is given by now equal to GM into R02 parallel with R04. Because this is 1 over, this will become 2 times RSS into GM3. Suppose if you assume R01 is equal, R02 and R04 are same, which is equal to, suppose if you write R02 is equal to R04 is equal to some R0, then I can write this as GM into R0, because this R02 parallel with R04 will become R0 by 2 multiplied by 2 into RSS into GM3. This finally reduces to GM into R0 and RSS into GM3 will be the CMRR magnet. CMRR magnet. We can see it has got a very huge CMRR because GM into R0 will be very large. Of course, RSS into GM3 will also be very large in quantity. So this way we can able to actually find out what is the CMRR of a transistor with active load. Active